In 2003, a Danish computer scientist named Peter Bro Miltersen cooked up a puzzle so brutal, he was sure it had no good answer. 100 lives, riding on a game that looks utterly, mathematically hopeless. He published it believing the prisoners were doomed, that no cleverness could save them. Then a colleague mentioned, almost casually over lunch, that there was a way out. Not a loophole, not a trick, a strategy, one that takes odds you'd need 30 zeros to write down and lifts them to something you'd genuinely bet on. Miltersen could hardly believe it. Mathematicians still call it one of the most counterintuitive results in all of probability. By the end of this video, you'll know the strategy, you'll see exactly why it works, and the weirdest part won't be that it works. The weirdest part is that it works without improving a single prisoner's odds. Stay with me. This one rewire my brain. Here's the game, and the rules matter, so let's be precise. There are 100 prisoners, numbered 1 to 100. In a sealed room, there are 100 closed boxes, also numbered 1 to 100. Inside each box is a slip of paper with one prisoner's number on it. Every number is in exactly one box, but the slips were shuffled completely at random. Slip 42 could be anywhere. One at a time, each prisoner walks in alone. They may open at most 50 boxes, half of them, looking for the slip with their own number. Find it, and they quietly walk out. Fail, and well. Then every box is closed again. Nothing can be moved, nothing marked, no notes left behind. And the prisoners cannot communicate once the first one steps inside. No codes, no signals. Now the brutal part. If every single prisoner finds their own number, they all go free. If even one of them fails, all 100 are executed. 100 people, and the whole group is only as lucky as its unluckiest member. They get one strategy meeting beforehand. That meeting is everything. Let's start the way any sensible prisoner would. Just open boxes at random. You walk in, you open 50 of the 100 boxes, half of them. Your number is hiding in one box, equally likely to be any of them. So your chance of finding it is exactly 1/2. A coin flip. Not bad for you. But you're not playing alone. Everyone has to win. 100 coin flips, and every single one has to come up heads. 1/2 multiplied by itself 100 times. Want to see what that number looks like? It's a decimal point, then 30 zeros, and then finally some digits. That's not a small chance. That's a chance so small it's basically a rounding error on impossible. You are more likely to win a national lottery jackpot 3 times in a row. For all practical purposes, 0%. The prisoners are dead. And here's the suffocating math behind it. Somebody, somewhere in that line of 100, is going to flip tails. Almost guaranteed. Random guessing doesn't fail because each prisoner is unlucky. It fails because 100 coin flips never all go your way. So that's the floor, effectively 0. But remember the strategy meeting. The prisoners get to agree on a plan before the first one walks in. No communication afterwards. No marking boxes. Each prisoner still opens just 50 boxes, still alone, still facing the same shuffled room. And yet, there exists a strategy that does astronomically better than random. Not a little better, not twice as good, astronomically. So here's your question. Pause and actually commit to a number. With the best possible strategy, what's the chance that all 100 prisoners survive? 1 in a million? 1 in 1,000? A brave 1%? Lock in your guess. Ready? The answer is just over 31%. Nearly 1 in 3. From 30 zeros to a number you take a bet on. Same room, same rules, same 50 boxes each. If that number feels impossible to you, good. It felt impossible to the man who invented the puzzle. The next few minutes are about earning it. Here is the entire strategy. It fits in one sentence. When you walk in, open the box labeled with your own number first. Inside is a slip. Whatever number is on that slip, open that box next. Read the new slip, go to that box, and keep following. That's it. No memorizing, no codes, no cleverness in a room. Just follow the chain wherever it leads. Let's watch prisoner 42 do it. She walks in and opens box 42. The slip inside says 17. So she opens box 17. The slip inside points somewhere else. She follows, box after box, slip after slip, like following arrows through the room. And on some box down that chain, the slip says 42, her number. She's done. On the surface, this looks like superstition. The slips are random. How is following them any better than guessing? Here's a hint that something deep is going on. The chain you're walking isn't random wandering. The shuffled room has a hidden structure, and this strategy rides it. Before this strategy can be good, it has to dodge two disasters. Disaster 1. You follow the chain and it just wanders forever, never reaching your slip. Disaster 2. The chain loops back on itself, circling through the same boxes, and your number isn't even in the circle. That second one sounds terrifying. Trapped on a merry-go-round that doesn't include your slip, burning your 50 opens going round and round. So pause on this, because it's the heart of the whole video. You start at the box with your own number and follow slip to box to slip. Why can you never get caught in a loop that doesn't contain your number? Think about what it would take for the chain to circle back somewhere. Got a theory? Here it is. For the chain to revisit some box, say box 17, a slip has to point to box 17. But there's exactly one slip in the whole room with 17 on it. Just one. And you already used it. That slip is how you got a box 17 in the first place. So no later slip can ever send you back there. Every box you visited is spent. Every box, that is except one. Your starting box, box 42. You didn't enter box 42 by following a slip. You walked in on your own for free. Slip 42 is still out there, somewhere down the chain, and used. So the only place this chain can ever close is back at your own front door. And the slip that closes it, the slip pointing to box 42, is slip 42, your number. Read that again in your head. Your slip isn't just somewhere on your chain. It is guaranteed to be the final link. Follow the arrows, and they cannot dead end, cannot trap you elsewhere. They must walk you in a closed circle that ends on exactly the slip you need. The only question in the entire game is whether that circle is short enough. 50 boxes or fewer, you live. 51 or more, you run out of opens, one slip short of home. Now, pull the camera back, because what's true for prisoner 42 is true for everyone. Every box points to another box. Every chain closes into a circle, which means the whole shuffled room secretly shatters into closed loops. Maybe one giant loop of 60 boxes, a loop of 30, a small loop of 9, and a box that points straight to itself. Every box lives on exactly one loop. No exceptions. That's not luck. That's just what a shuffle is, seen from the right angle. And look what the strategy really does. Every prisoner who walks in is dropped onto the one loop that contains their own slip, walking the same circle as everyone else on that loop, just starting from their own door. Everybody on a short loop finds their number with room to spare. Everybody on a loop longer than 50 fails. All of them. Every single member of that loop doomed together. So 100 separate gambles have collapsed into a single question about the room itself. When the slips were shuffled, did fate happen to build a loop longer than 50? If no, all 100 walk free. If yes, the prisoners on it die, and that's the whole game. 100 coin flips have become one roll of the dice. So how likely is the deadly giant loop? First, a tidy little fact. There could be at most one loop longer than 50. 2 of them would need more than 100 boxes, and the room only has 100. Now, for any size, call it some length bigger than 50. What's the chance the shuffle builds a loop of exactly that size? You can count it. Choose which boxes join the loop, arrange them around the circle, shuffle every one left over. Do that bookkeeping, and something gorgeous happens. Almost everything cancels. The chance of a loop of any exact length is simply 1 divided by that length. A loop of length 60? 1 in 60. Length 99? 1 in 99. So the chance the prisoners die is just the sum 1 over 51 plus 1 over 52 plus 1 over 53, all the way up to 1 over 100. 50 small fractions. Add them up. You get about 0.69, a 69% chance of doom, which means the chance they all survive is the leftover, about 31%. There it is. Not a simulation, not a hand wave, a sum you could do on a napkin. 31%, the number that sounded like a typo falling out of 50 fractions. Now hold on. Something should be bothering you. It bothered me for days. Take any single prisoner, our prisoner 42. With random guessing, her odds were 50%. With the chain strategy, what are her odds? Her loop is equally likely to be any length, 1 through 100. So 50 or shorter, exactly half the time. 50%. The strategy didn't help her at all. Not her, not prisoner 7, not a single one of the 100. Everyone's personal survival chance is still a coin flip. So what on earth did we just buy with all that cleverness? Here's the answer, and it's the deepest idea in this whole story. The strategy doesn't make anyone luckier. It makes them lucky and unlucky together. With random guessing, failures are sprinkled independently. Each prisoner flips their own private coin, and out of 100 flips, somebody always crashes. The group never survives. With the chain strategy, the prisoners have lashed their fates to the same mast, the shape of one shared room. Either the room has no giant loop, and every chain comes home, 100 wins all at once. Or it does, and the members of that loop fail together. The disaster lands in one concentrated pile. The total amount of luck hasn't changed. On average, 50 prisoners find their slip either way. The strategy just reorganizes the luck. It sweeps all the failure into the same unlucky worlds, leaving the other worlds perfectly clean. You can't raise the individuals, so you correlate them. That's the trick. That's the whole trick. And it's enough to turn 0 into 1 in 3. Don't take my word for any of this. Let's just run it. Here are random rooms, fresh shuffle every time, and 100 simulated prisoners playing the chain strategy in each one. Green room, everyone found their number. Amber room, a giant loop got them. Watch the survival rate as the trials pile up. 100 rooms, 1,000, 10,000. The rate wobbles, settles, and locks on, right around 31%, exactly where the napkin said. And look inside the amber rooms. Every failure has the same autopsy. It's never one prisoner having a bad day. It's one giant amber loop, 51 boxes or longer, dragging its whole crew down at once. And in the green rooms, often somebody walked 49 boxes and found their slip on the very last open. The strategy doesn't make it comfortable. It makes it possible. The math predicted it. The simulation obeys. That's how you know you understand something. One more twist of the knife. Suppose the prison grows. 1,000 prisoners, half 1,000 opens each. Surely now it collapses to 0? Run it. Still about 31%. 1,000,000 prisoners, each opening half a million boxes. The random guessing odds are now a decimal with 300,000 zeros. The chain strategy? Still just under 31%. The doom sum, those 50 fractions, grows into a famous shape, a slice of the harmonic series. And as the prison grows, that slice settles onto a constant, the natural log of 2, about 0.69 forever. So survival settles 2 at 1 minus log 2, just under 31%. For any size prison. For every size prison. Random guessing dies exponentially. The chain strategy doesn't die at all. That's not an improvement. That's a different universe. So what do you actually take home from Prison Puzzle? Your grandmother told you never to put all your eggs in one basket. The prisoners survive by doing exactly the opposite, on purpose. When you cannot raise anyone's individual odds, you can still choose how the failures clump. Spread the risk, and with 100 independent coin flips, somebody always loses. And here, one loss kills everyone. Concentrate the risk. Lash every fate to the same shared structure, and suddenly there are whole worlds where nobody loses at all. That's why this result floored Milterson, and why it still floors everyone who meets it. The strategy never touches the odds. It touches the correlation, and that turned out to be worth 30 zeros. Engineers think this way about backups that fail together. Teams think this way about all-or-nothing goals. Once you see don't improve the odds, organize them, you see it everywhere. Before you go, one last riddle. This one's for the comments. Same prison, same 100 boxes. But now the prisoners have a friend. One outsider who may sneak into the room before the game, open every box, look at everything, and swap the slips of just 2 boxes. That's all. Then the game runs as usual. Question: can that one tiny swap guarantee, not 31% guarantee, that all 100 prisoners survive? Think about loops. Think about what one swap does to a giant one. Tell me your answer below, and I'll see you in the next one. Bring 50 opens.